Okay, welcome to a session of circuit solving. So, your physics teacher tasked you with solving a series circuit. Well, we've got the solution. Any series circuit can be tabulated, calculated, and totally pulled apart with this simple method. So let's see what we've got. If you're in my class, we're going to do the circuit provided in Unit 10, Notes 9, Question 32. So let's start out with a source of potential difference, aka a battery. Here we go, big, little, put a couple hands on the end of that. And we're going to lump 3 resistors in series. So we'll put one down here, we'll put one over here, we'll put one up here. Notice we put hands on the ends of all of these. Those hands are where they connect. We'll have singular connections here, one loop. Boom, boom. Putting some wire in here. Okay. Now, here's the positive side of the battery. Here's the negative side of the battery. Though we know electrons do have net motion this way, thanks to Ben Franklin, we follow positive current. There we go. All right. Now, when you're dealing with a circuit, typically what you're provided, the tools you use to actually build a circuit, is a source of potential difference like a battery. So often the battery has a set value. At home, you got your AA's, your AAA's, maybe your C's, D's, or 9 volts. In this case, we're actually going to use a battery that represents the same potential difference you get in your wall outlet, although this is a DC circuit. So we're going to make this a 120 volt supply source. Then we're going to put 3 resistors on there. So the other things you control is often the resistance. The resistance depends largely on what the material is and how it's made. So we got over here, we'll put a 5 ohm resistor, we'll put a 15 ohm resistor, and we will put a 20 ohm resistor. We call these resistors 1, 2, 3. Okay. So here, there are 2 things you need to qualify right away. One is what sort of circuit it is. Because there is only one pathway for current, meaning it only has one possibility of where to go in the loop, we call this a series circuit. And we also notice that it has more than one resistor. So it's a series multi-resistor circuit. And when you see a multi-resistor circuit, who should you call on? You should call on your whole part VERP chart. Whole part VERP chart. What's that? Check it out. So you make yourself a little chart. Here's our chart. All right. So we say whole part. What we mean is we can consider the whole circuit altogether. So we make a column here called whole. Whole is really referring to the battery. It's also referring to the entire circuit. And then we have the parts. In this case, there are 1, 2, 3 resistors. Those are our 3 parts. So you can split this up and make this part 1, part 2, part 3. Okay. That's the whole part. Where's the VERP? Because we need a whole part VERP chart. There's the whole part VERP is V-I-R-P. There's your VERP. Whole part VERP chart. Those are actually going to be your rows. Also, there are other physical quantities you could solve for. This is our physics reference table. And in here, if you notice, we have, in addition to VERP, we also have, sometimes you're asked to solve for work or energy. Sometimes you're asked to solve for charge. Heck, you could even be asked to solve for time. We'll get to those if needed. Often, your questions can be answered with the whole part VERP chart. Okay, so one last piece you should add in here. If you notice in the reference table, there are both series circuit rules and there are parallel circuit rules. At the beginning, we defined this as a series circuit. It had only one pathway. So we want to actually establish that in our chart. Let's take this away. And just as a reminder, we're going to put a little SER over here, remind ourselves this is a series circuit. We are to follow the series circuit rules. Okay, enough setup. Let's get to the business. Plug in what you know. With certainty, we know certain things. We know certainty. That's a lot of certainty right there. Anyway, we know the battery and we know the resistors. So let's put them in there in our chart. We know that the battery has a potential difference of 120 volts. So that's the whole circuit. You put a 120V over here. You also know that the individual resistors are 5, 15, and 20 ohms. So we know their resistance. We come over here. So we have a 5 ohm. We have a 15 ohm. We have a 20 ohm. You notice I coordinated the 1, 2, 3 up top with the 1, 2, 3 in the chart. You will also see within the questions some comment along the lines of a circuit that obeys Ohm's law. It's kind of like a neglect friction comment in this course. Essentially that means you are free to use the equations on PRT4. More particularly that means we don't worry about the circuit getting hot. But when you solve these, if it obeys Ohm's law, that's great. You get to use all the equations that are on your reference table. So PRT4 is reference table page 4, and they will apply. All right, so let's go. We have all of our pieces set. Now it's time to start connecting the dots. Any old school thinkers here, this is like a game of Minesweeper. So, connect the dots. What do we see first? Well, we see we have 3 resistances. Is there something we could do with that? Actually, yes, there is. Come to your series circuit rule for resistance. Here it is. Notice that resistance sums in series to give you the Req, which is the total resistance. So let's do that. 20 ohms plus 15 ohms, that gives us 35 ohms, plus another 5 ohms, that gives us 40 ohms. So we actually get this Req, put a little comment for it down here. Req is going to be 5 ohms plus 15 ohms plus 20 ohms, which will give us our 40 ohms. Done. Now we know the total resistance of the circuit. Oh, you might be starting to pick up the pattern. What else could we do? Well, there are no other rows we can complete just yet, but we might be able to complete this column for whole. Notice we have the potential difference and the resistance. Well, how can we connect V and R? Well, actually, that brings us to our Ohm's law. Ohm's law, I've recommended you use your VIR pyramid. Easy way to not mess up your cross multiplication. So, here's your Ohm's law pyramid. Put the V on top, put an IR on the bottom, and whatever you're trying to solve for, in this case we don't know I, well, you would cover up that I. In a sense, you pull a little shade over it, and what's left over? V over R. So, actually, how are we going to solve this problem? By doing V over R. So the V is 120 volts, the R is 40 ohms, and so that gives you 120 over 40, 3 amperes. Great. Okay, 3 amperes. Now, what can we do? Aha! The current rule for a series circuit. Well, if the current in any one location is known, the current in all locations is known. Current through a series circuit is constant. So if we know it's 3 amperes up here, well, we just make use of I equals I1 equals I2 and so on. In this case, it's just 3 amperes equals 3 amperes equals and so on. Fill them in. 3 amps, 3 amps, 3 amps. Fantastic. Okay, now what? Hopefully you're seeing that. We know current, I, and we know resistance, R. We could know potential difference, V. This one actually brings us right back to our VIR pyramid. Here it is once again. However, this time we're looking for V. So take our little shade, cover the V. What are we left with? I times R. So in this case, we can do our I times R. The I for resistor 1 is 3 amps. The R is 5 ohms. And so that actually would give you 3 times 5, 15 volts. The next one would be 3 amps times 15 ohms. That'll give you 45 volts. And finally, through resistor 3, 3 amps times 20 ohms. That'll give you 60 volts. That's something you can do to check yourself. Since we know the potential difference or the potential drop across each of the individual resistors, does the potential difference rule hold, meaning the individual V's, do they add up to the total? And 60 plus 45, that's 105, plus 15, that's 120. Check. Okay, we're getting somewhere here. Now we've done the ver of VERP. Let's get to the P. How can we get power? Well, there are multiple equations for power. We have this multi-equation down here. However, you don't need to pick a complicated part. Here's our power multi-equation. Pick the easiest one of all. The VI, no squared, no division. Why not? That could work out. So P equals VI, you can do for the whole and for each of the individual parts. So let's check that out. You can set it up down here. P equals, for the whole, the V was 120 volts. The I was 3 amperes. 120 times 3, well, 12 times 3 is 36. 120 times 3, 360. Unit for power is watts. What? Watts. So the power total, 360 watts. If we do that same process through each of the resistors, you get, let's do the VI. This one is 15 volts times 3 amperes. That gives you 45 watts. Resistor 2, 45 volts times 3 amperes. Weightlifters, you're probably good at multiples of 45. So 45, 45, 90, 45, that's 135 watts. And then finally, resistor 3, 60 volts times 3 amperes. 6 times 3 is 18, so 60 times 3 is 180 watts. Okay, perfect. Now, if you wanted to solve any more, such as W or Q, you could do this. In fact, the process is identical. Here's the W equation. You can also use your Q from the current. But notice with regard to W, with work or energy, and with regard to charge, they have time. All of the terms have time. Which means, in order to solve these, you're going to have to be given some amount of time that the circuit is left on. So the process is identical. Pick an amount of time, or your teacher will pick an amount of time for you, and you will have that multiplier in there, and you'll get your answer. So that's no different than what we've been doing. Now, there are a few trends to notice up here, worth noting. Let's see, this page is getting a little crazy over here. Let's move our equations out of the way, clean up, and let's put the trends perhaps that we've noticed here. Nice little list of trends. All right, things to notice. Number one, anytime you go across a row, you end up using the series circuit rules. So if you want to connect across a row, you have to end up using these right here, these series circuits rules. Okay? Anytime you want to go through a column, suppose across a row could go either way, through a column in this chart, generally you're going to use the rules you'll make use of are Ohm's law, that's your VIR pyramid, and also your power and energy equations. So all that's been provided to you in your reference table. You'll see that here. Your Ohm's law is this one. Here's your power and your energy equations. So you're essentially empowered to do everything as long as you take those trends seriously. Now, in our reference table, maybe others are different, but in our reference table, the trend involving or equation guiding power as a series circuit rule is not actually listed. But you can pick it up from this. So power as a series circuit rule, it's not listed in our reference table. There's one for potential difference, there's one for current, there's one for resistance, but there's none for power. Do we see one? Well, there's a mathematical base for this, very easy. Power is V times I. So V adds and I stays the same. So power should, actually, if you want to look at that mathematically over here, power is VI, and then you could say power is, so V plus V plus V, and I stays the same for all of them, I. You could pull out that common factor of I, and you will see that, oh, wait a minute, power should just add 2, and in fact, it does. Check it out over here. 45 plus 135 gives you 180. 180 plus 180, 18 plus 18 gives you 360. So there's a new series circuit rule that's the total power. It's just going to be P1 plus P2 plus P3 and so on. Conveniently works out that way. Sometimes it'll make it quicker just to realize that. Okay, that's enough for now. So any series circuit can be solved with this process. Set up your whole part VERP chart, and though at times you may feel like this is overkill, there is no chance you miss what anyone is looking for. As long as you fill in your physical quantities, follow the rules, you can't miss anything. And so the question you get on an assessment, though it may seem small, what is the power through resistor 2? It would be a mistake for you to just simply say, okay, P equals VI, let me just start running a couple numbers in there and be done with it. The chart answers all questions about this series circuit, and so the chart really is art. Whole part VERP chart for life.